Welcome back to the live course. I'm Brittany Brady with O'Reilly Media, and I will be your facilitator for today. A quick reminder, we are recording today's session. We will have it within 24 to 48 hours. You'll receive an email when it's available. During the course, you can complete our feedback survey at any time. It's accessible if you click on the More at the top right corner of the screen. It will also pop up automatically when we finish today's session. Please take a moment to fill it out and let us know your thoughts about today's live course. We really appreciate it. With that, I'll hand it over to Benjamin to get started with day 3.
All right, thank you so much. Welcome back to day number 3. Just a couple of words from my end. Brittany just mentioned the survey form. It would be super useful to me as well to understand kind of like your feedback, what you've been missing potentially, and what went well, what didn't go so well, to further polish the content that we already have. So that would be super useful. Today, we'll start talking about the troubleshooting pods and containers in more detail. I already mentioned that in the domain we started with yesterday on application observability, and I believe it's called troubleshooting. If I'm not mistaken, I can bring it back up. And then we'll transition over to the next bigger domain, which is somewhat of a catch-all bucket, I would say. So in that bucket, we will be talking about what happens when you make a call to the API server of Kubernetes. Then we'll briefly talk about RBAC in that context as well. And let me bring up my screen here so you can see what I'm talking about. Then we'll briefly talk about what operators are and how CRDs come into the mix with operators. Then we'll talk about resource management. We kind of talked about it yesterday in the context of the metric server, but I definitely want to expand on that. We'll talk about different configuration options, more specifically config maps and secrets. And then lastly, we'll also talk about some security settings you can provide to your applications. And then lastly, as I mentioned, networking is the biggest topic left at that point. So here we'll talk about 3 different Kubernetes primitives: the service, the network policy, and the ingress. Those are all going to be part of that section. So I think that's going to be an important one. So I definitely want to make sure that we have, say, an hour or 1.5 hours left for that section specifically. All right, before we jump back in, do you have any more questions from your end? If not, we'll be starting right here just to give you some troubleshooting techniques we've already been touching on. So here's a question: is it worth setting up a Vim during the exam? For example, creating a Vim RC file with line numbers or auto indent, or is that a waste of exam time? I think it's a waste of time. Vim is already set up for you. So you will have that available from the get-go. I don't think it makes sense to further configure it because in the end, you're just going to basically modify a couple of things of existing YAML files, potentially write your own ones. But overall, I wouldn't spend time on it. You will definitely need all of those 2 hours just for solving the problems. I wouldn't spend too much time on it. All right, thank you for the question. Then I would say let's jump back into the content and more specifically on troubleshooting. Wanted to give you a couple of techniques that are useful. Not only for the exam, but also for running Kubernetes in production. So as application developers, we will deploy things into production at some point. And then things will unfortunately not always go down the happy path. So we'll have to make sure that we can identify root causes and then also know how to fix it. So what I want to provide to you here is a couple of commands scenarios we've partially been talking about before that are super helpful to identify those issues. In the exam, you may be faced with those troubleshooting scenarios as well. So one typical question could be, or task could be, have a look at the objects in namespace XYZ. One of them is failing. Just make sure that it is like transitioning back into the running state again. And that is something that you need to be comfortable with. And that includes also identifying existing objects and being able to basically retrieve details for them. Now you can see here on the screenshot, there could be error statuses like the ones we've seen in, I believe, exercise number 2 already, where we have a scenario where a container image cannot be pulled from a registry, either because you mistyped the name or the tag, or simply the container image does not exist in that container registry. You would see something like error image pull. That is one of the more typical error messages you would see in this context. So for the most part, you will want to strive for running as the status. However, I would say it doesn't necessarily mean that the application is fully functional. We still potentially have to dig in, identify if the application is running properly, if we can connect to external systems and things like that. Now, the Kubernetes documentation is not super detailed on individual error status messages. Here are just a couple of them that I run into fairly often. Already mentioned the image pull back off and the error image pull. They basically mean the same thing. One will actually transition into the other status sooner or later after retrying a couple of times. Then we have the crash loop backoff. That is a fairly common error status that you would usually get if the application of the process running inside of the container crashed for some reason, or if the command you're running isn't configured properly, or if something's not available in that environment. So that usually points to an application like failing for some reason or not being configured properly. And then we have the create container config error. That is going to come into play if you're referencing a config map or a secret object by name. However, that name does not exist or only exists in a different namespace. Now, this list here is definitely not conclusive. There are plenty more error messages that you potentially can see. Obviously, that will also change with new versions of Kubernetes potentially, where things may be renamed or added onto or even removed. So unfortunately, not well documented. And if you search for it on the web, you get some nuggets here and there, but it's not super conclusive, I would say. Now, if you run into those status messages that you would usually identify as a failure or error, what I would usually do is to have a look at what I mentioned as the event log before. So the event log is a portion of the output when you run the describe command that can give us additional detailed information on what failed when starting up the pod. So you can see here in this case, apparently we're referencing a secret object by name, and this secret object does not exist. So this will give you more hints on what to look for, what the potential root cause could be. Now, sometimes you also want to get those events not only just for one single pod, but potentially for all pods in a namespace. You can use the get events command to get a quick rundown of what's happening in the current namespace. In this case, that would be the default namespace. Now, obviously, in production, you'll likely want to use a monitoring tool, not kube control necessarily, but for the purpose of the exam, or if you just want to really go down low level, that is really what you can use here on the kube control level. Independent of the status that you may see for your pod, you may want to also have a look at the log files. So for example, let's say you see something is failing, you definitely want to see if there was an error message produced by your application while starting up. And we've already looked at the logs command before, but I just wanted to mention it in this context again, because it's super helpful for troubleshooting purposes as well. Now, the last thing that we may potentially want to do is to open an interactive shell into the container and navigate the file system or have a look at the process list. In those cases, we could use the exec command to achieve that, but only if you were to have a shell that ships with the container specifically. Now, you may know that some containers do not ship with the shell at all for security reasons, and or also to make the image much smaller than it would be otherwise when shipping with a shell, but for the most part, it would be for security reasons. So how do you troubleshoot those kinds of containers? Those kind of containers are usually or oftentimes referred to as distro-less containers. Those are the ones that do not provide a shell. You will oftentimes find those in the container images provided by Google. So if you look at the GCR, so the Google Cloud Registry, the container registry from Google, you will definitely find some public images that are pretty prominent there that don't necessarily ship with a shell. And you can see here that we cannot open an interactive shell. We would get an error message because the shell does not exist or the process for opening the shell does not exist. So how do you actually troubleshoot those kinds of scenarios? Definitely possible as well. Thankfully, in kubectl, we have the debug command. So the debug command had been introduced in kubectl at some point. It's now a production-ready feature, so to say. It didn't used to be. It was still in beta. But as of now, you can actually use it to effectively create what they call a ephemeral container. So an ephemeral container is a container that only exists for the time of actually debugging your application code or whatever you want to troubleshoot in your containers. So effectively, it creates a disposable container, so effectively a copy of what you had before. But it uses a different base image here. So you can provide a base image that actually does come with a shell. So in this case, I decided to go with BusyBox, but you can definitely use a different one. And then you can use that to basically identify and troubleshoot the underlying issue. And keep in mind, when you exit out of that interactive shell of the ephemeral container, the container will be gone. One more command that I want to mention here, which is sometimes useful if you're dealing with long log files or something that you want to compare visually. Sometimes you can't quite see the issue in the terminal window, and therefore you may want to transfer the file that you want to look at onto your host machine. So basically from the container onto your host machine. And what you can do here is to use the CP command. So CP stands for copy. And what we can do with the command is to copy a file, and more specifically, a tar file out of the container onto your host file. Just be aware you can only copy tar files, not any other files. So if you need something, you still need to tar it up first. And therefore, that is how you can transfer it. All right, so let's have a look at the next exercise here. That is going to be, let's see where we stand, number 20. So here I already prepared for you a pod.yaml file. And this pod will have an issue when you start it up. So have a look at it and identify the root cause and potentially think about how you could effectively fix the underlying issue. So I'll give you maybe 10 minutes for that one. And in the meantime, I'm going to answer your questions. Let's have a look at the solution here. I will go back here to my terminal window and I will go to number 20 here. And you may have seen I already had this pod.yaml file in place. Effectively, here we are running one single container, and the container uses a Node.js based container image. Ultimately, in the command, we're running the node command, and the node command will effectively create or derive the current timestamp. We'll try to write it to that file specifically in the string form. And then if there was any kind of issue, we will write it to standard error, as you can see here. And it will do so in a while loop. So this is happening, I believe, multiple times. So let's have a look at what's going to happen when I create the pod here. As you can see, the container is currently in the process of being created. We'll wait until it's ready. Looks like we do have a running status. So at least on the surface level, you could potentially assume that there's no issue with running the application, but that's not necessarily a given. So it's always a good idea to also have a look at the log files produced by the application or process you're running. And as you can see here, we actually did get an error message where it says that it can't open this file here specifically. This could basically point to the directory not being existent, or maybe potentially permissions or something else. So let's have a look at what we could do here to investigate why this file cannot be written to. And what we can do here is to use the exec command. Let's say you didn't have a look at the actual container image before. And you can see here bash is not available. binsh is not available. So this one is a container image that does not ship with a shell. So if you look at that, in fact, this is coming from Google. This is just one of the indicators that could tell. But in the end, you would have to have a look at the details of the container image itself. All right, so what we can do here is to use the debug command potentially. And what we can say here, we want to interactively debug the date recorder pod. We'll want to use an image. And as mentioned in the group chat, the image is a container image that either contains the shell or some troubleshooting tools that you need potentially for the purpose of diving deeper. So for example, you may need curl or some diff tool, whatever you want to use here that you think is useful. And then the target here would be the container image that we want to basically have a look at. And then lastly, we can also provide another option. I hadn't mentioned that before yet. If you also want to inspect the processes of the container we want to troubleshoot, then you can share them also with the ephemeral container. All right, so we're now in the ephemeral container. What we're going to try here is to navigate to this directory specifically. So we want to go to root temp. I would assume that root does exist. It does exist. So if you see where we are, that does exist, but apparently the temp directory is not being created automatically by the logic here. So fs, which is the file system library in Node.js, does not apparently create the directory automatically. That is something that the logic would have to do in the first place. So checking if the folder does exist. If it does not exist, create it first and then write to the file. This could be part of the command that I'm running here, so that could fix it potentially. Or alternatively, if you wanted to make sure that the directory exists and not necessarily on the root file system of the container, we already learned about how to achieve that. We would usually then mount a volume. So that would be your fix here. So if you were to now create the directory, just be aware that that is only temporary. If you were to restart the pod, this directory would be gone. And given that we also shared the processes, we should be able to have a look at, the process list here. So you can see we are running or had been running this command. So that's part of the process list. If you would have not used that command line option, this one here specifically, share processes, you would not be able to see the process list. All right, so that's what we wanted to do here. Do you have any more questions on troubleshooting? And obviously, troubleshooting more complex scenarios takes a little bit of time, but the commands that I've been providing to you should definitely be good enough for you to find out what the issue is in pods in the exam environment. And in summary, I would say, get familiar with the get and describe command, just to identify, first of all, the status of the pod. Know how to have a look at the event log with the describe command. Then be able to get or retrieve the logs for a specific container. And then lastly, also know how to open an interactive shell or how to run a command against a specific container. So here's a question. Can you explain this a bit more? When you say this, I'm not quite sure what you're referring to here. How are we inspecting the Debian with BusyBox? So effectively, you're creating almost like a copy of the original container that you want to inspect. And then ultimately, you're using a different container image that you want to use that comes with troubleshooting tools or that comes with a shell so that you can actually have a look at it. Here's a question. Do you need to be comfortable with bash scripts to take the exam? It used to be the case. I'm not quite sure how it's going to look like now. I'm not quite sure how the questions changed in the past year or two. I believe last time I took the exam was a year or so ago. So maybe something came in with that. So I can never quite answer your questions if it will look like that when you take the exam. But I think it would be useful to be familiar with bash, not only for the purpose of the exam, but also to be able to use it in your own workplace. So sooner or later, you'll have to use bash either way. So whether that's just being comfortable with running commands from the terminal window, but then also some tooling that you need for troubleshooting purposes. May it be like curl, get, navigating file systems and things like that. All those kinds of things may come into play when it comes down to troubleshooting. And then troubleshooting in terms of like, here's one more common troubleshooting also comes down to understanding how Kubernetes works. Here we are just looking at troubleshooting from the perspective of an application developer. There's far more troubleshooting involved if you work as an administrator, because then you will have to understand where certain configuration files live, what kind of cluster components you have, how they're configured, and those kinds of things, and more specifically, security-specific configurations. So I think it is far more involved on that end versus as application developer, where you just have to basically troubleshoot, at least if you work in a silo, if you have to troubleshoot just the applications running inside of containers for the most part, and the networking portion of it. So if you can talk between microservices running in Kubernetes, or if you exposed it properly. But that is something that we'll still have a look at a little bit later. All right. So let's talk about the next bigger domain here on application environment configuration and security. That's a far bigger topic, and I feel they just threw in a bunch of stuff that didn't quite fit with other topics as well. So I would call this almost a catch-all bucket. So here in the first section, we're going to talk about custom resource definitions and how they're usually provided by operators. So we'll have a look at those two concepts and how you can use them in Kubernetes and basically what their role is. We'll briefly also explore how you can define your own CRDs and basically create your custom objects from it. Then we'll have a look at role-based access control. So that's a way to basically restrict who is allowed to do what in the Kubernetes cluster. I think that's a fairly important topic simply because in Kubernetes, by default, many things don't have any permissions by default, or you don't necessarily want to give admin permissions to anyone involved interacting with the Kubernetes cluster. Thankfully, they lock things down by default quite a bit for service accounts in the meantime, and that is what we're going to have a look at as well. Then we'll have a look at resource management on the container level, and then I will mention a couple of other Kubernetes primitives, like the range limit and the resource quota. We'll also have a look at security-specific configuration, and lastly, we'll also talk about how to define configuration data that then should be consumed by applications running inside of containers. So the first topic I want to mention here is on custom resource definitions. So that is one of the topics that had been added with the last overhaul of the curriculum. And you may ask yourself, why do we need custom resource definitions, or even what are they? Can't we just go with the built-in Kubernetes API or the primitives that we already have in place? Well, there may be use cases where you need to introduce your own custom resource definitions because core Kubernetes simply doesn't fulfill specific use cases. And there are many use cases, for example, that are not covered by default by core Kubernetes because it's simply not a core competency of Kubernetes. So you can think of Kubernetes as a platform that you can enhance based on your custom requirements. And one way is to enhance the platform is by adding your own custom resource definition. So effectively, a custom resource definition means that you're introducing your own Kubernetes primitive with your own schema, your own specification that you can then use for fulfilling your own custom requirements. Now, oftentimes the custom resource definition is mentioned in the context of the operator pattern. So the operator is effectively the combination between the custom resource definition and a controller, because the custom resource definition by itself doesn't do anything. So effectively, when we introduce a custom resource definition and create an object for that custom resource definition or that follows that schema, you have new objects sitting in your Kubernetes cluster. However, they don't really do anything for you. They're just there. You can inspect them. You can interact with them the same way as we've done so far with kube control, but there's no reaction to their state in any kind of form. And that is really the main purpose of such a controller. So the controller is the portion of the operator that it usually ships with that will inspect the state of your custom resource definition objects and will then run some specific logic based on that. Now let's have a look at one specific example pretty soon on the next slide. But before we do so, wanted to show you those different moving parts in the form of a visualization. So the first thing, if you wanted to define your own CRDs, you would have to create a schema first. So it would effectively be a YAML file that describes that this custom resource definition has this kind of kind. It uses this group or this version. It defines multiple attributes that we can specify that can be set when you instantiate the object for it. And then based on that schema, once we basically installed that into the Kubernetes cluster, we will then be able to create CRD type kind of objects, which will use that kind and set the values for the attributes defined by the schema. Then lastly here, as you can see, the controller will have a look at those objects and then react to it. Now, ultimately, this will basically tie into the Kubernetes API. So to be able to look at those CRDs, you have to make a call to the Kubernetes API. And that is something that we'll actually talk about in the next section when we speak about the interaction of pretty much any client with the API server cluster component in Kubernetes. So let me give you one example here that is dreamed up, really. It's primarily one of the things that that kind of explains one use case for wanting to use a CRD. So let's say we are building web-based applications that are being deployed with a deployment object. And then you expose the application using a service object. And what you want to make sure that every time you deploy an application, you want to run a quick smoke test to an endpoint exposed by that web-based application. Now, that's not necessarily a capability built in or an automatism built into Kubernetes. Well, you could use the container probes, but ultimately, maybe we want to do something more here. We not only want to see if that was successful, but then also record the status of your application based on the result of that smoke test and send that information maybe to an external service outside of Kubernetes, maybe just a database, and then you want to render the status of your applications on a dashboard. So that's definitely something that you could achieve with the controller logic. And ultimately, what we want to build here is the CRDs that represent that smoke test. So the CRD here would define the endpoint that we want to call, and the controller would be the portion that basically has a look at the smoke test. So if there's a new smoke test object, it would be able to read the definition of that object, and then, or the status of that object, or the state, I should probably say state of that object, and then we'll make a call to the external database or whatever you want to implement here. And CRD and controller together could be shipped as an operator. So let me show you one example how we could define such a smoke test. And you can see here on the left-hand side on the slide, that is a custom resource definition. So effectively, this is the schema that you want to use. This is how you want your objects that follow the schema to be represented. Now, down at the bottom, you can actually see the kind that we want to introduce, in this case, smoke test. And you can see there are also some other names, plural, singular, short names. Those are primarily being used by kubectl, so that when you run, for example, kubectl get smoke tests, it knows that we're talking about this specific custom resource definition or the objects that follow it. Then up there, we also have the group and the version that we will have to spell out when we create an object from that schema. And then lastly, there's also a list of properties that we can spell out. In this case, what you can see here is just one single property. I had to cut it a little short because otherwise this definition would be too long and likely not readable anymore. But ultimately, the attribute that I'm introducing here is the service of type string, which you can see right here. So that is one of the properties that I want to make available to any of the consumers. So once you basically install this custom resource definition, you would then be able to create the objects that use that specific kind that we just introduced. Now you can see here API version is the combination of group and version. And together, that is what we need to use here in the API version assignment. And underneath the spec section, you will see all the properties that we defined in that custom schema. And one of them is the service. So ultimately, the service here could be the DNS name of that service. We have a URL context path, which is /health to be able to make that call. And this should be configurable depending on the web-based application. And then potentially, you may also want to introduce things like timeouts, retries, socket connection timeouts, maybe. to be able to make multiple calls if the first one would be failing. So that is definitely super useful if you wanted to expand on it. But you can see you can craft it in the way that you think makes sense for your use case. Well, we of course have to install both of those or have to run the apply or create command for both of those YAML files. The first one is basically the CRD, and the second one would be the YAML file that represents our object here. Once you install a CRD, we would be able to also have a look at it in the list of API resources. So there you should find it now, and you can interact with it in the same kind of way as if it were to be a core Kubernetes primitive. And one more thing to mention here, the controller implementation is not going to be part of the CKAD. All they want you to understand is how to interact with CRDs. And let me see if I have one in place on my machine here. I'm not sure if I installed something here, but if I were to look for API resources, let's see if I have something here. I don't think I installed something recently. Probably shut it down in the meantime, but you would see your own CRD as part of this API resources list. And then once you see it, you can basically interact with it the same kind of way. And that means with the kget command, for example, if that were to be my CRD, you can use describe. And also, if it would have a specific name, my object, we can delete those objects. So that is how it could look like. One more side note here, the controller implementation usually involves bringing in a Kubernetes client library. Depending on the programming language that you're choosing to use here, this could be Go, Python, Java. You would choose from one of those client libraries which help you with interacting when making the call to the API server. So that basically abstracts at least some of that logic for the HTTPS communication. Let's see what else we could say here. But yeah, that is pretty much it. But the controller implementation out of scope simply because it would require you to understand a programming language or potentially a specific one. So I think that would be hard to verify if you are going into the exam or if you're the person trying to grade the exam. So here's a question. The 21 exercise asks to create a CRD from scratch. Why is this part of the exercises? I wanted to expand a little bit more on the knowledge to put it into context. What I could have done here as well is to install a operator and then let you interact with the CRDs that come with the operator. Yes, it goes beyond what you need to understand, but I wanted to make it a little bit more than just what you need exactly for the CKAD. So that's the main reason. If you feel like we should only exactly do what the CKAD asks of you, feel free to add that to the survey form. I can definitely tweak that a little bit more, but I think it's better to have a little bit more knowledge on how the CRD is actually defined if you want to do this on your own, because otherwise you'll just see that there is a new CRD, but you don't know exactly how that is being specified. So I think it's better to take that additional step to understand it a little bit better. Here's somebody saying one of the most important capabilities in the Kubernetes community is the CRD. Yeah, the CRD is being used by many of the operators out there. So if you use something more custom, you will definitely want to interact with it potentially. And you will see many of the use cases here, which, for example, is coming from Argo CD or Prometheus, whatever, what have you, each of which bring in their own CRDs. So you will see them quite a bit. So not necessarily just the ones that are Kubernetes core primitives, but potentially other ones. So I would say, given that the number 21 is not exactly what you need to understand for the exam, I would say do this as a homework. It lets you interact with the CRD once it has been created. I believe the solution potentially provides you with the corresponding YAML manifests, so you don't have to like necessarily create them from scratch. You can basically just instantiate them, apply them, and then interact with them, and then create an object for it. But ultimately here you can see that is a full-fledged custom resource definition that not only describes one property, but multiple of them, including their types. In this case, it's a representation of a backup that we want to run periodically. And then down here, we have a actual instantiation of that CRD. And that is how you can see how those pieces fit together in more detail. You can see here for the backup, we can define a cron expression. We can see which pod we will want to inspect, probably also a container name. So this is all hypothetical, just to make you more comfortable with the process, but ultimately that is what you could do. I personally have not seen a question on CRDs in my exams yet, so maybe they just added this topic for completeness sake. Maybe it's different or going to be different when I take it the next time, probably in a year or half a year or so. I have to retake it, but I'd be happy if I would hear from somebody that took the exam recently, if that was a topic that was actually asked for, potentially not even covered. But it could also be like randomized in terms of the questions. So therefore, I'm not fully in the loop of what's available in the catalog of questions there. All right, so let's transition over to authentication and authorization before we then go into the next coffee break. This section is going to be mostly about the interaction from a client with the API server. And this could either be kube control, it could be a visual dashboard of sorts, it could be just curl that makes a call to the API server endpoints. It could be a process of kinds or a tool that you build yourself. So any interaction that you will want to go through with Kubernetes usually will be funneled through the API server. And that is where we have the tie-in with authentication, authorization, and admission control. So that is what we're going to touch on in this example. Just to show you the high-level overview of the process of what's happening here. You can see here API server is the cluster component in the control plane node or the control plane nodes. And anytime we make a call to the API server with any client, so for example, if we were to run kube control get pods, it will effectively emit a HTTPS call or request to the API server. And this request will not be processed right away. It actually has to pass through 3 different phases, which are authentication, authorization, and admission control. The same thing is true for external processes, anything else that you might be building yourself. Usually for those kinds of tools, you would have to assign a service account for multiple reasons. One of the reasons is that every time we make a call to the API server, we do have to authenticate against it. And that means we have to send credentials with that call to basically prove that the identity that we are pretending to be, that we are really that identity. So effectively in authentication, we first verify, do the credentials you provided or the process provided is valid, and is it known to the Kubernetes cluster. Then we have the authorization phase, which effectively verifies if the operation that you requested to run is allowed for your identity that you're authenticated with. So for example, if you said, I want to delete the deployment with a specific name, are you even allowed to do it? And then lastly, we have the admission control phase. That is a phase where we can further massage or verify the data being sent with that request, and then do something or act upon it. So oftentimes what you will find is that tools in the CNCF landscape that are about security or governance will tie specifically into the admission control phase. For example, OPA, Gatekeeper, Caverno, those are tools that lets you verify data that had been sent with the request and will then potentially do something. It will validate it, or it will potentially even add configuration to it, but that is completely part or abstracted by those tools. Now, either way, the request will only be processed if you actually pass all of these 3 phases. If not, the request would be rejected. So that is just a little summary here. So let me talk about authentication a little bit more in the context of kube control, and what's going to be important to you as the exam taker or somebody that actually uses kube control on a day-to-day basis. So I mentioned before, every time we make a call with kube control, we will have to know the endpoint of the API server that we want to talk to, and we need to provide the credentials so that we can actually authenticate with that API server. And if you're using kube control specifically, that information is embedded in a so-called kubeconfig file, which you can find in your user home directory .kube. And inside of there should be, at least by default, a file named config. There could also be multiple kubeconfig files that you may want to configure and merge them together. A little bit out of scope, but ultimately, if you are just beginning with a simple setup, there would only be one single kubeconfig file. And you can see here that is effectively a YAML manifest file, which has primarily, I would say, like 3 or 4 sections. Section number 1 is the definition of the cluster. So the cluster is effectively the pointer to the API server, so the endpoint that we want to talk to. Then we have a user or multiple users, as you can see there. So the user in my case is my username and the client certificate for my user, which is embedded here in that file. Side note, if you are using a cloud provider, there's definitely additional tooling that lets you add new entries to this kubeconfig file. You don't usually have to modify it manually. So that can be happening through those AWS tools, for example, or different cloud providers. And then lastly, we also have a so-called context, which effectively is the combination of the cluster and the user, and optionally the namespace that you want to interact on. So you may remember from day number 1, there was a command set context, which lets you set a namespace. So this lets you configure the namespace and sets it as a default for a specific context. So when we're talking about switching contexts, we're basically talking about this one here specifically. So basically the combination of the API server endpoint and the user you want to use to interact with it. Now you can also see there's a current context. You can switch between multiple contexts. For example, if you need to interact with multiple Kubernetes clusters, but you can switch between them with a simple command. And I believe I have those commands here on the slide, which are built into the kube control executable. Now, there are multiple commands and subcommands here, mostly work based off of the config command. You can see here config view simply renders the contents of the kubeconfig file. We can show which current context is set for me. We can switch to a different context with use context. And there's also set context that I mentioned earlier that lets you set the namespace. And then lastly, we can also verify which context I'm currently in. There may be more subcommands which you can explore on your own. Those are just some fairly common ones. And that is effectively how the API server knows what credentials to verify when you make a call using kube control. So it's not the fact that if you make a call with kube control, that there's no authentication happening. Even for Minikube, authentication is happening every time, but basically this has been populated in the first place. And if I were to have a look at my file here, so .cube config, you will see there are multiple entries here for things. Even AWS is in here. So that's definitely something that you can configure. All right, so far, that's all I wanted to mention about authentication. Here's one more question. Context is for the username or for the namespace. It's a combination of cluster, user, and potentially namespace altogether. So it's basically the aggregate of all of those three. Because remember, when you need to talk to an API server, you need to know which endpoint to talk to. So you need to have that. That is the cluster. You need to authenticate every time you make a call to the API server. That is the user, including the credentials. And then lastly, if you do want to set a different namespace than the default namespace, then that can be set for the context as well. So there's a combination of those three components. All right, so for authentication, there could be far more said, specifically for integrating external identity management tools and systems that you may already have in place. Completely out of scope for the CKAD, and it's not even being covered by the CKA in more detail. But generally speaking, that is what you need to understand, at least on a high level, on authentication. It's also unlikely that you will be asked to configure kubeconfig in any kind of form. I think, again, that is one of the topics that they just added for completeness sake, because you have to understand it, but will they test for it? Unlikely, I would say. The next topic here is going to be on role-based access control, and that is going to be basically on the next phase in that processing, which will be on authorization. And before we jump into that, I would say let's take a 5-minute break. I will definitely want to go through an exercise on this topic as well. So we'll probably spend like 20, 30 minutes on this topic in more detail, because it's definitely an important one. But before we do so, let's bring up my 5-minute timer. I'll take a 5-minute break, and then we'll jump right back into it. But do let me know if you have any questions in the meantime. All right, so let's get back to the authorization topic. And the feature in Kubernetes we want to use to basically restrict access control to certain resources in Kubernetes is called a role-based access control, in short, RBAC. We've seen where the phase actually ties into when we look at the processing phases in the visualization. But generally speaking here, what we can define is policies that let us define for users, groups, or service accounts what operation is allowed or disallowed for specific API resources. I would say this is an important topic to pretty much anyone using Kubernetes. For security reasons, primarily, more so for the administrator of a Kubernetes administrator. So therefore, make sure that you understand this topic properly. It's usually not a good idea to give everybody admin permissions. It may be convenient in the beginning when you get started with Kubernetes, but sooner or later, pretty early on, hopefully, you will want to define those RBAC permissions and different kinds of users and groups that should get just a limited set of permissions. So probably application developers would not need the same permissions as administrators for a Kubernetes cluster, because they usually don't interact with the maintenance part of Kubernetes clusters, for example, with nodes as much and things like that. So that usually should be reserved for admins. And that is how you can basically group those permissions based on certain stakeholder groups. There are three different key components that you need to understand for RBAC, and that is the subject, API resources, and the verbs. So effectively, RBAC or RBAC rules or policies are basically the aggregation of those three different components. So what we want to say here is for users, groups, and service accounts, we want to allow access to certain API resources. This could be a pod, config map, secret, deployment service, those kinds of things. And for each of those API resources, we can grant certain operations to be allowed. In the context of RBAC, they're oftentimes referred to as verbs. Now you can see here, create, list, watch, delete. Effectively, those will boil down to the underlying HTTP methods that you would be using here, for example, like post, get, and so on. Just to put it into the context of one visualization here, to model those three components, we need to understand 2 more / 4 more Kubernetes primitives. Let's get started with the role and the role binding. So the role is effectively a definition or the combination of the API resources and the verbs you want to grant access for. The role is always based on a specific namespace. So therefore, it will only be applicable to that specific namespace the role lives in. And the same thing is true for the role binding. It is also namespace-based, and it will effectively tie in the different kinds of subjects with a reference to the role. Now, under certain conditions, you will want to grant permissions on the cluster level, so across all namespaces, and that is when you would use the cluster role primitive or the cluster role binding primitive. Kind of depends on your use case. So how wide do you want to make those permissions? I would say it's a good idea to get started with just the role and the role binding, just to apply those permissions to one single namespace. So let me show you the imperative command first. As you can see here, we are using the create role command. And here we have the combination of one or many verbs plus one or many resources. Pretty straightforward. If you look at this from the perspective of a YAML manifest, you can see that looks relatively straightforward as well. So the kind is role, and then underneath the rules section, we do have one or many of those rules. And you can see here, I have 2 different rules in this case, one for deployments and one for pods and services. The main reason why they are different, why they cannot be just one single rule, is that pods and services live in the default API group, whereas the deployment lives in the apps API group. You may remember that from when we talked about the deployments. If you were to use the API group with an empty string for all of those 3 API resources, then the permissions wouldn't work properly. Unfortunately, last time I checked, there's no verification whether you have the right assignment of certain resources to API groups. Personally, I think there should be a validation built in when you create the object, but at the moment, I believe, or at least last time I tried it, that was not the case, and that is the main reason why you need to define 2 different rules here. We can inspect those roles as usual, and they give you the detailed configuration of them. And then also to show you the role binding. The role binding, as I mentioned before, is the combination of a reference to a role by its name, and then one or many subjects. So in this case, I'm only assigning one single subject, that is the user John Doe. There are also command line options for a group assignment, as well as a service account assignment. And just keep in mind, the role can be bound to not one single user. It could be bound to multiple users, multiple groups, and multiple service accounts, or a combination of them. Just to show you how this looks like here in the form of a YAML manifest, you can see here underneath the role reference, we have a reference to the name of the role that we want to use here. And then under subjects, as I mentioned before, there could be multiple users, service accounts, or groups. In this case, I'm just showing one single user. Skip over that. So that is basically how you can define those permissions using the role and the role binding. And more specifically in the context of a human user driving a visual dashboard or kube control. But there are definitely use cases where you will want to build additional tooling or where you potentially want to make a call to an endpoint of the API server. For example, you will want to find something out about your Kubernetes cluster from a CI/CD process, which completely lives out of, or could completely live out of Kubernetes. And therefore, that also needs to be authenticated, needs to be authorized, and so on. So to be able to even have the information for external processes, to basically authenticate and to get a reference to the identity within Kubernetes, we have to use a so-called service account. So the service account is basically an assignment of a Kubernetes object that we will want to assign to anything that's non-human request, basically any tool that you may be building, or a simple curl command that you may want to run, or yeah, those kinds of things. So the service account, once you create the object, and it will show you pretty soon how to create it in the default, or at least as a minimal set of configuration, it looks pretty straightforward. That's why I'm not going to show it here right now. But in the context of RBAC, you can see that we can bind it into the whole concept as well. So we can say, for example, bind this service account into the role binding. So instead of defining a user, we would define a service account. I also wanted to mention here that the service account can not only be used outside of the Kubernetes cluster, but also by processes running in the pod in Kubernetes itself. And independent on whether you make a call to an API endpoint from within the Kubernetes cluster or outside of it, you always have to make the call against the API server. And that also includes authentication, authorization, and admission control. Now, let me show you one example on how we can actually make a call to an API server endpoint using a curl command, for example, from within the Kubernetes cluster itself. The first thing we need to know is the endpoint of the API server. I think that makes complete sense. This could either be the cluster internal IP address of the API server component, plus the port number that has been used here. But there's thankfully a convenient way to basically get a reference to this, which is called the Kubernetes service. Now, we haven't talked about the service concept yet. That is going to come within the next hour or two. But ultimately, it provides you with an endpoint that we can use. So basically a DNS name that is far more convenient than using a cluster internal IP address and a port number. Now, the Kubernetes service will be created for any Kubernetes cluster. Now, you can see here that if I were to run CKAD services in the default namespace, you can see this Kubernetes endpoint does exist. Sorry, I shouldn't say endpoint. This Kubernetes service does exist. And it basically points to the IP address and the port of the API server. So that's super useful and can be used to make calls to it from within the Kubernetes cluster. And you can see here, I'm creating a pod, or more specifically, a temporary pod that runs the curl command to, in this case, make a call to an endpoint. And this endpoint effectively gives you the list of pods in the namespace K97. So that is just one example of an API endpoint that is exposed by the API server, but there are far more endpoints that you can explore in the Kubernetes documentation. Now, I mentioned before that we can also make calls, for example, with a process like curl from within a pod, and that is exactly what I'm going to go for here. On the left-hand side, you can see the definition of a service account in the form of a YAML manifest. looks pretty straightforward. That is just the standard configuration that comes with some functionality that is completely configurable, but I will show that to you a little bit later. By the way, any kind of security features of the service account that are more advanced are going to be outside of the scope for the CKAD. That's more a topic for the security specialist, by the way. So once we create the service account, we can assign it to a pod using its name. And how we do that is underneath spec service account name. And once we do that, we get one feature out of the box right away, which is the automatic mounting of a volume to the container that consumes it, or really for all containers within the pod, that will provide us with access to a authentication token. Now, the service account will generate an authentication token automatically for us, and will then provide it to the underlying container, which is available at the mount point var run secrets Kubernetes IO service account, and then there should be a token file. Now, this is one of the options that I mentioned before that is configurable. If you want to turn this off, you can, but again, outside of scope for the CKAD certification. Now, we can use the contents of that token file to basically use it as a way to authenticate against the API server. Now, just to put it all together here, that is the pod that I've shown to you before that assigns the service account with the name SA API. And then in the command that I'm running here, I'm using curl specifically. I'm assigning the contents of the token file, which I read with the cat bash command, using a header that I will send with the request. And then I will make a call to an API server endpoint, and I will do this every 10 seconds in a loop. So that is basically how we can send authentication information if you wanted to make a call to the API server and then make sure that we can authenticate against it. One more thing to show you here in this context, which is the tie-in with the role binding. You can see here that I'm defining the service account underneath the subjects section. And to basically define the permissions for this service account, we have to use a cluster role, not just a role. The main reason being is that by default, Kubernetes introduced cluster roles that will disallow pretty much any custom service account to have any permissions for security reasons. And those are simply defined across all namespaces. So therefore, if you wanted to create any permissions for a service account, you will have to go with a cluster role instead of a just plain out role that applies to a single namespace. So with that, let's give this a try. You will see this is a bit more involved. It would be exercise number 22, but I think it's an important one. So I will give you, say maybe even 12 minutes on that one. And I will check in with you maybe after 10 minutes to see if you could solve this. The endpoint, I don't necessarily have it here, but I can provide it to you so you don't have to look it up in the documentation. I should probably provide that as part of the instructions, simply because it's probably not going to be super relevant to you. You can always look it up on your end, but let me provide that. So you don't have to spend time on that necessarily. So the endpoint we want to call is going to be this one. So we want to get the list of services, which is available through this endpoint in the default namespace. So you may have guessed it from the structure of the URL, but ultimately we want to make this call every 10 seconds, I believe. I think that's probably what I mentioned here, or just make it periodically, and then see if you set the right permissions to even be allowed to make that call using the service account. So I'll turn on my timer here, 12 minutes, and then we'll show the demo on my screen. let's have a look at the solution here. We'll go ahead and create the service account in the first place. But before we do so, let me create the namespace here. And namespace in this case was supposed to be called T23. I will use the imperative command to create a service account. And that could look as simple as this one here. And now within that namespace, we should have a service account. -n T23. As you can see here, we have API call. Then next up, I want to get ready my pod, which will make the call to the API server endpoint. I'm in the wrong directory. So let me make sure I'm navigating to the right one so you know where we are when you watch the recording. So here I want to say create a pod. And I'll simply just get that from the solution in this case. This actually looks fairly similar to what I've shown to you on screen. And you can see that we are going to use the service account token provided by the service account that we mounted up here by name. Okay, we'll save that. Okay, apply -f pod.yaml. And we should have a running pod here now. And of course, the right namespace, T23. And you can see it's running. Let's also have a look at the logs of this. Okay, log. That doesn't need to be here. We can also follow this flow of log messages using the -f command line option. So I believe in my example, in my pod, I'm making a call every 5 or 10 seconds. So a new entry would be added every time. You can see that my service account with the name API call in the namespace T23 is not allowed to make that call. So if I were to add some spaces here, I think you should be able to see the response here. And the reason why that is happening is that the default permissions for service accounts that we create on our end are basically very limited, and we're not allowed to make a call to the services endpoint. But what we can do here is that we can tie that into RBAC and make sure that I have the right permissions for that call specifically. So what we're going to do here, we are going to create a cluster role. I'm just going to get that from the solution here. The only operation we want to run here is to list services. None other operations should be allowed. You can easily expand that if you wanted to, but keep it as constrained as possible for security reasons. Don't simply just grant all permissions to all API resources. That is definitely a security risk. So we'll create that object from it. And then lastly, down here, we also want to create the role binding. I'm going to copy paste that in here. So the main difference here is that under subjects, I'm defining my service account, which references that service account in a specific namespace. And then down here, I'm referencing the cluster role by its name. So that is the one that we just created before. All right, so we created the RBAC mechanics here. Now let's go back and have a look at the results. And what you should find is that we now get back the proper results. So you can see here in the default namespace, we get back the list of services, and the list of services contains the Kubernetes service. That is the one that I just mentioned here before. So we do get a response now. We have the right permissions, and you can play around with those permissions in more detail if you want to. But that basically demonstrates to you how we can define the permissions for a service account. And this can potentially become a question in the exam as well. All right, any more questions on RBAC? Just looking at my clock, we still have 20 minutes, so we'll definitely want to spend some additional time on that. Oh, where's this one coming from? Okay. All right, I don't see any questions as of now. Then I would say we'll spend about 20 minutes on this section here on resource management, why that is important and why you should use it in your own applications. And then when we look towards the admin level features, which are resource quotas and limit ranges, just wanted to give you a high level overview on what they provide to you. You personally probably don't have to create those objects. This would be more an activity by the admin of your cluster, but you may feel the effects of having them in your namespace. So therefore, you will want to know how they roughly function. So the first topic we want to talk about here is the definition of the minimum and the maximum amount of resources that we want to grant or ask for in a container. And I think that's an important metric to have, simply because we want to right size how much resources your application is expected to consume in general. That is something that you would usually find out during application development. Oftentimes, I shouldn't say oftentimes, sometimes application developers write load tests and they can figure out roughly or get an idea of how much CPU and memory is required by your application. But if you don't do that, and many people are under pressure nowadays to deliver software, you can definitely have a look at the runtime values when you monitor production or staging environment, and then make adjustments based on that. So it's a suggested or recommended practice to effectively define those resources for any of your containers when you specify them in your pods. Then on the admin side of things, we have two Kubernetes primitives that you can use to enforce the usage of resources. That is the resource quota and the limit range. The resource quota basically constrains the number of resources. For example, I want to constrain my namespace to allow for 4 pods to be created. Or we can say, what is the average usage across all pods of CPU and memory resources. So if that's something that you want to govern, the resource quota could be super useful. And then the limit range is a primitive that has been introduced a little bit later, but it's effectively a policy that not only lets you constrain certain resource types, for example, pod, or system volume claim, and so on, but it can also basically assign or automatically assign resource allocations when you create the object and you didn't necessarily specify those constraints on your end. That is usually a good option if you wanted to further massage the data or the configuration of a pod, for example, where an application developer said, I want to create this pod with 2 containers, but they didn't specify the resource requests and limits. And in those cases, you can add them automatically using the limit range. By the way, side note, the limit range actually does tie into admission control, into that phase that I mentioned before. So therefore, that is where I see one of the use case in admission control where the data being sent with the request is massaged or changed later on. So limit range can effectively automatically add resource requests and limits as something that you can specify. Now, resource units, you may have seen them in Kubernetes, don't necessarily follow the typical metrics that we know from software engineering, like megabytes, kilobytes, bytes, and gigabytes. Oftentimes what we see here is that we measure CPU resources in millicores, and then memory resources are measured in bytes. So don't get confused by the different notation. That's basically what that means. So let me show you how we can define the minimum and the maximum amount of resources for a container. So within the container definition, we have a resources section, which has 2 different attributes. One is requests for the minimum amount of resources. And then we have limits, which is the maximum amount of resources. Now, there are different kinds of resource types that we can specify. Among them are CPU and memory. And one more side note here, the resource requests will actually tie in with the functionality or the algorithm that the Kubernetes scheduler cluster component looks at. It will actually look at that number and determine based on the requests of resources if it can fulfill or where it can basically place that pod on one specific worker node that can actually fulfill those requirements. If none of the nodes would be able to effectively run that pod because you asked for more CPU or memory, then you likely will see that an error status is mentioned for that pod. For example, pod exceeds free CPU or pod exceeds free memory. This simply just shows it in a visualization. Don't want to necessarily go through it. This is just a overview for reference. So if you want to understand how we can define certain things here for the resource requests, it gives you a couple of examples. And then just to show you one full context example, the resources block here is part of the container definition. You don't have to come up with a new Kubernetes primitive. It simply just ties in to the usual configuration that we've seen before. Now, similarly, we can also define the resource limits, and the resource limits have the same range of resource types we can specify. It's a good idea to basically define your limits as well, simply because you don't want your application to hold on to more memory or consume more memory or use more CPU than you think it should be using. So it basically creates an upper boundary for resource consumption. Depending on the container runtime that you have installed on that worker node or potentially even on the control plane node, it will handle that situation based on its own implementation. It's fairly common that a container runtime would terminate that application process and would simply just shut it down when you reach that upper boundary. But ultimately, we want to basically avoid situations where, for example, when you have a memory leak, that more and more memory would be consumed. And at some point of time, you end up consuming all the memory available on that host machine, and specifically on that worker node. That is definitely something we want to avoid with setting this. This is just for reference. Here's one example. So that shouldn't be super surprising. Side note, this is more for reference here. You can, at any given point of time, look up which node a pod runs on by using the get pod command or the describe command. As part of the output, you should find that specific node being mentioned. In this case, first command here, this pod runs on worker node 3. And then if you go the inverse route, if you want to look at the node itself, you can also describe the node. And if you do have the metric server installed, not only will you see the pods that are running on it, but you will also see the current consumption of certain resources. So this one puts it all together. I'm going to skip over it. And I think this one is relatively straightforward. So do this one as a homework. Basically here, you just need to set the resources section. Just wanted to mention a couple of words here about the resource quota and the limit range and how they actually play out in practice. So effectively, when we're talking about these, the setting requests CPU or requests memory, basically, this will always define the amount of resources across all pods in a non-terminal state in that specific namespace. So effectively, the sum of consumption of CPU and memory across all of those pods. We can also define a certain number of objects. So for example, we can say we can only allow to create 5 different secret objects. I'm not quite sure why you would want to do that, but ultimately it's one way to basically have a hard limit that can be enforced automatically. So here's one example for such a resource quota. I don't think you necessarily need to create it on your end because I see this more as a admin specific primitive. But ultimately, what's more important is if you were to see an error message that would tell you something that is being enforced. So one of the things that will be enforced if you set the resource requests and limits in the resource quota is that it will enforce automatically that the pod you want to create will have to specify those numbers. So request CPU and memory, as well as limits CPU and memory, will then be enforced. If you don't define it, it will basically give you that error message. And it, by the way, it will not let you create the pod object. Also, if you're requesting more CPU and memory for requests and limits than granted by that resource quota, you may also see the following error message that you exceeded the quota, and that gives you the indication that you should stick within those boundaries or ask your admin to expand on it. There's also a column that you will see that shows you the current usage of CPU, memory, and really anything that you can set in the resource quota. You can see that here underneath the used column. And we'll skip over that. And then just to compare that briefly with the limit range. So the limit range lets you also define defaults. So I think that's a killer feature that you can use if you want to enforce the usage of resource requests and limits independent of whether application developers set it or not. Let me show you one example here. That is how the limit range looks like. So the limit range has a section that lets you define defaults, and those defaults would be assigned automatically. But it will basically also enforce minimum and maximum resource ranges for a specific type of resource. So in this case, it's actually a container. It's not really a resource in that sense on the Kubernetes level, but that is how they basically modeled it. And just to show you how this actually plays out, so let's say you created a pod that does not define resource requests and limits. As a result, once you created the pod, the limit range will come in, it will massage the data, and will add those numbers that we specified as defaults automatically. So that is at least to get a good baseline. It's also possible that we want to create a pod that exceeds the limits, and therefore that will be effectively enforced here by the limit range as well. And there are a couple of other use cases that you can go through in this exercise if you want to dive a little bit deeper. So I would say we'll skip over that simply because it's going to be also more of an admin feature. Just be aware that if you see an error message that I've shown to you here before, it doesn't necessarily tell you which object enforces this, but I would suggest to you, have a look at the list of limit range and resource quotas, which you can actually do at any given point of time using the following commands. So you can say resource quota, and you can see there's none of those. And for limit range, you can do something similar. If you notice that you cannot create a pod for some reason, have a look at those two objects. They may be involved in that specifically. All right. Any more questions? I would say maybe we'll take the 5-minute break now before we jump into the next bigger section. And the next section is going to be on defining configuration data with the help of 2 new primitives we haven't really talked about yet, which are the config map and the secret. All right. I don't see any questions. So I would say let's do the 5-minute break, and then we'll reconvene in a second. All right, so let's jump into the next bigger section here on config maps and secrets. 1 second here. Maybe let me do one thing before we jump in. I want to refresh my browser just to make sure that my audio is still on. All right, can you hear me now? Should be working now, I think. If not, I may have to log in again. Hello, test 1, 2, 3. Okay, awesome. Good deal. So let me back up again. I don't know what you heard before. So basically, we talked about the definition of environment variables before, just inline in the container definition. But oftentimes we actually do have the need to basically centralize the definition of configuration data into one location so that we can reuse it across multiple different kinds of pods. So oftentimes we actually face common configuration data, for example, like connection URLs to an external service, maybe credentials for authenticating against it. And there's really no point in copy pasting the same kind of logic or data across multiple different pod definitions. So therefore, Kubernetes came up with the concept of config maps and secrets. Effectively, config maps and secrets are objects you can create that have their own lifecycle that define simply just configuration data. And usually those are defined within those objects in the form of key value pairs. Now, you can think of the difference between a config map and a secret more semantically. It's more really about how you think about that kind of data that you want to store inside of them. Don't necessarily think that because the secret primitive is called secret, that the values stored inside of it are encrypted or secret in that sense. That is not really the case. Secrets have not been designed that way. So effectively, when we talk about config maps, we want to store plain text values that are usually reflected as connection URLs, runtime flags, maybe a username if you want to have that in plain text. Then the secret is effectively meant for storing sensitive data like passwords, API keys, SSL certificates, and so on. But keep in mind, the values that are stored in the secret object are only base64 encoded. So base64 encoding is not encryption. At any given point of time, you can decode those values with a simple base64 tool. And anyone really with access to those objects will be able to basically get the plain text values, even though they may reflect passwords, API keys, and SSL certificates. Now, oftentimes, organizations that are more security conscious will not store data in plain text in Kubernetes itself. They may be using a different password manager of sorts or secret manager, for example, HashiCorp Vault or AWS Secret Manager and the like, which can be integrated into Kubernetes using a operator. So there's an operator out there, and that is one of the reasons why I mentioned the operator concept before as well, is that it can integrate functionality from external systems into Kubernetes, and it's not a core built-in Kubernetes feature, but it can be added to the platform, so to say. One more side note, if you are the admin of a Kubernetes cluster, or if you're want to give your admin a hint, it's likely also a good idea to encrypt the data in etcd, more specifically the data for config maps and secrets. By default, when you set up your Kubernetes cluster, they are not encrypted, and therefore that is completely configurable. The configuration of etcd out of scope for the exam, just want to mention here as a side note. Now, the config map and the secrets that we create in the form of objects can be mounted to a container or can be injected into a container. The assumption here would be that the application code either reads those values as environment variables, or the application reads it from a mount path on a volume. So depending on how your application code has been structured, that basically determines which kind of method you will go for. But generally speaking, both methods, mounting as a volume and injecting as an environment variable, is available for config maps and secrets the same kind of way. So let me show you some examples for the config map and the secret, how we can create them and how they can be used within the container. What you see here on screen is the imperative command for creating config maps. The key value pairs can either be sourced directly from the command line as parameters, or you can point that command to a file that then can be used to evaluate those key value pairs and then store them in that config map. Now, there are a couple of differences between those configuration options. One option I want to mention here specifically is the difference between from env file and the difference to from file. Main difference here is that from env file assumes that the file that you're pointing to already has key value pairs inside of them. So each of them separated with an equal sign, and each of those key value pairs on a new line. And it will then use those to effectively derive the key value pairs. But that is different if you were to use from file. When you use from file, then the name of the file that you're pointing to will become the key name within the config map, and then the contents of the file will become the underlying value assigned to that key. Let me show you one or a couple of examples actually in the context of the imperative command as well as the representation in YAML. You can see here is just a very simple imperative command that assigns two key value pairs from the command line. And that in turn will create something similar to what you see on screen here. That is a config map representation that has two different key value pairs. You can see here that I'm following the naming convention for environment variables. That is, by the way, not enforced whatsoever by the config map or by Kubernetes. It's simply a convenient way to basically represent an environment variable, how you would usually do it, but there's nothing enforcing it on the Kubernetes level. So you could also go with lowercase if you wanted to. So here's one example how we can then consume the environment variables or the config map as environment variables. I would say that is almost human readable. So we want to consume environment variables from a reference to a config map with the name dbconfig. And as a result, once the pod is running and has a container in place, you will be able to have a look at those environment variables. So your application code would then use its internal libraries to effectively read those environment variables and will then use them to configure the application at runtime. Now you can reconfigure the keys of existing config maps if you have the need for it. This may be the case if a config map has been around for a couple of years and you cannot easily just change the contents of that config map anymore because you have a bunch of legacy applications that use the old key and its notation, and you don't necessarily want to change everything across the board. If you want to adapt to a new name for that key, you can definitely do so. And you can see one example of that notation here. That is something that you can easily look up in the Kubernetes documentation, but effectively here, we're just mapping the database underscore URL to a uppercase kind of version that then should be made available from within the container. Here's one example where I actually create a config map from a file. In this case, it's a more structured file, a JSON file, which represents data that we want to read from the application code. If we want to read that from application code, I think it makes sense to preserve the formatting and the structure of that JSON file. And that is exactly what we're doing here. That is effectively the result, or if you want to start with this approach here with the YAML file to basically use the file name as the key and then the contents will become a multi-line YAML value. And of course, we will want to inject it into the container. I mentioned a couple of different volume types yesterday. You can see here the volume type config map is the volume type that we're using here. Effectively, it just points to the name of a config map, and then we'll make it available on a specific mount path from within the container. And you can see here on the right side, when we open an interactive shell, that the contents of that file are still preserved. One more side note, if you were to change the data within a config map, that data is not automatically reloaded within containers that already consume it. That is something that you would have to implement yourself in your application code, or alternatively, you would have to restart the pod that consumes it, but there's no ingrained logic in Kubernetes that would reload changed values in your config map or secret. With that, let's give this a try. This would be exercise number 26, and I will just bring this up here. I'll give this 10 minutes, and then we'll have a look at the solution. Do let me know if you have any questions. All right, so let's have a look at the solution here. Oops. We want to go to number 26. And you can see I have the application.yaml file right here. Let's have a brief look at it. It's simply just a structure in YAML. And what we're going to do now, we are going to first create the config map, and then we'll mount it as a volume to the underlying pod we want to create. So the first thing we want to do here is to say pod, create config map. And this one I apparently still have in my history. You can see I'm pointing it to this file using the command line option from file. And that effectively means that I will use this as the key, and then the contents of the file will become the assigned value. Now I can have a look at the config map in the form of YAML. And you can see that is exactly what happened here. So the file name is application.yaml, and then you can see a multi-line assignment of a value, which preserved the contents of that YAML file. All right, so we created that. Now the next thing we want to do is to create the pod, and I will make this real quick. I'm just going to show you the solution for that one. We've already been talking about volumes quite a bit, and I don't want to necessarily have to type this out. But the most important part here is that we want to assign the config map volume type. And then up here, we'll simply just mount it to a specific mount path. Let's create it. And what we should find then is the pod will be running at some point, hopefully. So it's called backend. So let's exec into it. Backend. And then we want to go into the right location, which was etc config. And then here we should find our file that we added. So you can see here application.yaml, and then the contents are preserved as is. So that's super useful if you want to then read this logic, read this data from the logic of the application to further configure it. So I would say the volume mount is a pretty good option for when you want to deal with structured data, which may contain a long list of different configuration options. And from your application code, you will want to run some logic, which will then evaluate portions of it. All right, any more questions on the config map? Not, I will also show you some examples on how to handle secret data. and not being so secret, given that it is only going to be base64 encoded. And you can see that the imperative command for secrets looks somewhat similar to what we've seen for the config map. However, it has another sub option. And there are 3 different sub options as of now: generic, Docker registry, and TLS. Those will basically define what kind of secret we want to represent. So to represent any kind of generic secret, you would go with the generic option. But if you wanted to have something more specific, you could go with TLS or Docker registry. So Docker registry would be used for representing the credentials in a Docker configuration file. You want to turn that into a secret object, and TLS to represent SSL certificates. So that is definitely something that we can do with those kinds of options. Now there's a little bit a disjoint configuration here between the kubectl CLI tool and how it is being represented in the YAML manifest. You can see that the type inside of the YAML manifest will be represented different than the option given on the command line. Primarily, you will likely want to look at the type within the YAML. I should probably rename this to YAML, type in YAML. So we'll make it a little bit more clear. But you can see here there are 3 different types that basically mean the same thing as a generic Docker registry and TLS. Now there are other types that are available that are not shown here on screen, which are currently also not supported with subcommand options from the kubectl command line tool. There is a flag called --type that lets you set a different kind of type. But as of now, that is how this looks a little bit clunky. That's the main reason. Well, the generic options are pretty much the same ones as we've seen for the config map, so we'll skip over them. I mentioned before that there are different kinds of secret types apart from the ones that I've just shown to you. There's also a way to basically represent basic authentication information, so that would be username and password. As a way to represent SSH authentication. And lastly, you can see those are more internal ones. If you want to represent a service account token or a token for a node to bootstrap it, those are, I would say, Kubernetes internal secret representations. Those are not ones that you would usually have to deal with as application developer, but ultimately they exist as a secret type. Now let me show you the usage of the imperative and the declarative option again. You can see here on screen, we are using almost the same command we've seen for the config map. The main difference here is that I need to add generic. The most important thing to understand about the imperative command is that it will turn the value that you provide here on the command line or from within files that you're pointing to, it will turn it into base64 encoded value automatically. So what you see here on the right-hand side is the result of running the imperative command. So instead of having the string secret, we will actually go with C, N, J, CM, capital UH. But if you do want to basically start with the YAML manifest in the first place, you will have to assign the base64 encoded value. So that's simply something that you have to keep in mind when you craft your own YAML manifest for secrets. Now let me show you 2 different options here again for consuming the secret object. This looks very much similar to what we've seen for the config map. So environment variables from a reference to a secret with the name live secret. And what you'll get inside of the container is in fact the base64 decoded value. Then on the file side of things, here's one example how that could be represented. You can actually see that I'm using a specific type assignment, which is a command line option for the secret. to represent SSH authentication information. And then lastly, here's one example for representing that file in the form of a volume or added to a volume. You can see here that the volume type is secret, and then the volume mount is similar to what we've seen before. Now, given that the data for a secret is not encrypted anyway, I guess the Kubernetes community gave in, or the team itself, and said, well, why don't we care at all about this base64 encoding, except if we wanted to shorten a string or obfuscate it? Why don't we allow to assign the plain text data as well? And you can see here string data is another attribute that you can use to assign the key value pairs. At runtime, when you create the object, those will still be turned into a base64 encoded value. And the question just came up here, why do we allow even secrets to be in plain text? It is definitely a security concern. And that is why I mentioned earlier that many other companies will likely bring in an external secret manager. I already mentioned AWS Secret Manager and HashiCorp Vault as an example. And those could all be integrated into Kubernetes and represented in the form of an encrypted value using the operator called external secrets. So if you go to this one, you will see it actually does come with a bunch of CRDs. And of course, the controller, just to show you one example, pinning this back to the CRD concept, you can see there's a secret store, which basically defines the location where to find the secrets, in this case, AWS Secret Manager, I guess. And then there's an external secret, so a representation of an external secret. So this is something that you can tie into Kubernetes if you wanted to. And most companies, I would say, probably externalize secrets outside of Kubernetes. One more thing as a side note, either way, whether you use an external secret manager or not, you will want to also set permissions properly for secrets specifically, and therefore assign the right RBAC permissions so that you will basically not grant access to those secret objects to anyone with access to the Kubernetes cluster. So here's a question. The only reason you would use secrets as described would be for non-production. Yeah, likely. If you want the secret values that you store inside of it to be encrypted, then you don't have any other option. Side note, there's another project called Bitnami Secrets, Sealed Secrets, which lets you represent the secrets in the form of an encrypted form. But as of now, that's an external project. You can play around with that, but I would say most companies, not only for the reason of Kubernetes not providing encrypted secrets, but because they already have a secret manager in place that they trust, they will simply just integrate that into Kubernetes. And that's the main reason. But sealed secrets is another way to achieve encrypted secrets in Kubernetes that doesn't involve an external secret manager, but it uses a different kind of method. I believe it's somewhat production ready, or it is production ready for the most part, but you will have to dive deeper into it. And by the way, it's not going to be part of the exam for sure. So in the exam, we are only testing effectively the main difference between config map and secret, how to create them, and a little bit about the base64 encoding, and then how to consume those config maps and secrets from a pod. But that's pretty much how far coverage goes. Maybe at some point of time, the Kubernetes community will also support core Kubernetes functionality in that realm that will have encrypted values. I think from their perspective, they don't want to have the additional overhead of dealing with the whole handling of those, and that is probably one of the reasons why they delegated that knowledge to the consumers. So again, think of Kubernetes as a platform, not necessarily as a full-fledged solution for all problems. And therefore, it's likely better where the organization or the company that uses Kubernetes decides on a different product for storing secrets, and then you integrate those products into Kubernetes. All right, any more questions on secrets? I do have a secret, I have an exercise for the secret concept, but I would say that's somewhat similar to using the config map. So I would say if that's something you want to play around with, definitely do this as a homework. And here's a question that I hadn't seen before. How does HashiCorp Vault work with secrets? This would go beyond the coverage of this course. I used to run a Vault course, which isn't being run anymore on the O'Reilly platform. I can point you to the materials of that course if you want to. I can do that during the next break, but generally speaking, it effectively is an external system. It encrypts the data that you want to store inside of it. But that would be a course by itself, just covering HashiCorp Vault. All right, any more questions before we still talk about the security context, before we then transition over to the networking concepts in Kubernetes? And we'll try to keep the security context somewhat light. All right, I see no questions right now. So effectively, we haven't really talked much about security options or configuration in Kubernetes yet. I would say it's almost outside of scope for the CKAD certification. If you want to dive deeper, it's definitely a better fit for the security specialist certification, which is the advanced certification after taking or passing the CKA. But here we want to give you some initial knowledge on what configuration options we have on the container level that lets us set privilege and access control for a pod. Now, every pod can come with a set of attributes that we can set, which consist of either configuring Linux capabilities, file access control, privileges for parent processes, the host system, whether you want to run the container with root user or not. So those things are all enforceable. If you wanted to set those attributes, you can. And there are usually two different options. One is directly underneath the specs section, if you use the security context block. And the other one is individually on a per container level, which allows you to set some attributes as well. Some attributes are settable on the pod level, where some other ones are settable on the container level. But there's also a slight overlap between some of those attributes, which we can set on the pod and the container level. Let me show you some of those examples here that we can set. So I mentioned before, Linux capabilities. We can also tie in some of these tools like AppArmor, SecComp. We can set file system controls, those kinds of things. So let me show you some examples of what could be said and what the level should be. Now, if you want to have a quick reference to the different attributes, you can definitely just click on those ones here. Those are links that point to the API of Kubernetes or the documentation, which describe the different kind of properties and how they can be supported here on either the pod level, or the second one is the one that will set the properties on the container level. So if you need a quick reference in the exam, I would suggest having a look at the relevant documentation. Let me show you some examples on how we can set some of those attributes. So let's say we wanted to set a security context for all containers in that pod. What you could do here is to achieve that is by setting the security context directly underneath the spec section. And what this basically means is that it will apply to all the containers in the pod definition. Now, in this case, we are setting the file system group to 3000. So whenever you were to create a new file, it would automatically assign that file system group to the file that we created. So that is one of the options. Wanted to show you another option here, which is the enforcement of running the container as non-root user. We all know that running the container with the root user is usually not a good idea for security reasons. But you can see here that we can basically enforce that by setting run as non-root to either false or true. Now you can actually see here that I define the same attribute on the pod level as well as the container level. And effectively what this means is that you can override a setting that has been provided on the pod level already. Now, this is primarily useful if you're dealing with more than a single container. It doesn't make too much sense if you just have one single container, because then you would only define it in one area. But what I wanted to demonstrate here, because it didn't fit on the screen anymore, is that you can basically define it on both levels, and the container level definition always wins. And then as a result, when you run a specific container, you will see we can inspect the user ID that has been used to run the container. And in this case, this is running as a non-root user, assuming that the container image already defines what user we are running with. So I would say, why don't we give this one a try? So you have a rough idea on what can be set here, and then we'll transition over to the networking topic. And here we want to basically set the file system group. We want to see how that actually plays out in practice. So I'll make this relatively short. Let's make this 8 minutes. I think that probably doesn't take too long. All you need to do is to set the security context and then inspect how that behaves at runtime. All right, so let's have a brief look here. I'll make this really short. I will go to the right number, which in this case was 28. And what we are going to do here, I'm going to get started by setting up a pod with a volume assigned to it. I'm just going to copy paste it from the solution here. So you can see volume type is empty-dir, mount path is data test. And now we want to define a couple of options on the pod level. So we can go here and add the security context. And here we'll say we'll want to run as a specific user, 1000. By the way, this user, I believe, has been defined within this container image. So if you look at the container file for that container image, it will probably tell you about it. We'll also want to run as a group. And lastly, the file system group set to 2000. We'll save that kapply-f pod.yaml. And then let's see how this actually played out. Let's make sure we can open a shell to it. And what we should find, we should be able to navigate to data test. That is the volume mount path. We'll touch a file, logs.test. And let's have a look at it. And you can see that the file system group ID and user has been set. It might not be the case that it switched the user. Was it UID or something else? I would have to check here. ID, that's what it is. And you can see user ID is 1000 and the other options that I said here before. All right, any more questions on the security context? So I think the most important thing to understand about the security context is where to find the right attributes when you need to set them in the Kubernetes documentation. And then that the pod security context can be set on the pod level as well as the container level, but the container level always takes precedence. So that is roughly what you need to understand. If you really wanted to play around with those options, how they behave at runtime, then you would have to set up the right scenario. This may be something that you may want to explore in the context of the CKS certification, if that's something that you're planning to take at a later point of time. But generally speaking, that is about the coverage that you need to understand for the CKAD. All right, so looking at the clock, I would say before we transition over into the last domain for today, services and networking, why don't we take a 5-minute break now, and then we can start afresh after the break. And then the first topic we'll be speaking about is the service Kubernetes primitive, why we need it, how to configure it, what the different kinds of services are that we can set. So I think that's going to be exciting. Alrighty, so last hour of the course for today, what are we going to talk about? So we'll be talking about the service concept. So I mentioned before that the pod will expose a IP address that we can use to communicate from one pod to another one. This IP address is only available from within the Kubernetes cluster. However, there's one downfall to it. This IP address can change every time we were to restart the pod, and therefore the main reason why we needed a service concept, or one of the reasons why we needed a service concept, and we'll dive deeper into services, how to use them, how to configure them in this section. And we'll briefly talk about how to troubleshoot services. So if something goes wrong with its configuration, what do you need to look at? Then we'll talk about the ingress primitive, how that one is different from the service and why you would need it. And then lastly, we'll talk about network policies. You can think of network policies as firewall rules for the communication between multiple pods. So that is what we have left in this course for today. If you have any questions already, feel free to line them up so I can see them early on. I will try to carve out some additional time at the end. So in case there were any questions, we can definitely address those at a later point of time. So let's get started by talking about the service concept. And I already mentioned the main driver for the service. So if you want to model microservices within your Kubernetes cluster, at some point of time, they will need to communicate with one another. It's oftentimes not the case. They're just standing by themselves. Oftentimes, one microservice needs to talk to another one and back and forth. So therefore, we need to have some sort of stable network interface that we can rely on over time, that we only need to configure once and then can use it across the board. And that is really the main reason why we have the service concept. The service concept, or the service primitive, has a couple of configuration options that you need to understand before we can effectively use it. And one of the concepts, again, is label selection. Now you can probably see why label selection is such an important concept, because not only is it being used in the deployment concept or primitive, it's also being used in the service primitive. So effectively, in the service, we say we want to route traffic to any pod that has the corresponding label assignment, in this case, tier front end. And therefore, in this visualization, the network traffic would only be routed to pod number 1, but not pod number 2. Now, there's another portion to the traffic routing that I want to mention here, which is the port assignment and the port mapping. So within the service, we have to assign 2 different ports at a minimum. One is the incoming port. So any network traffic or requests that want to reach the service will have to use that port. at least from within the Kubernetes cluster. And then we also have a target port. The target port I oftentimes categorize as the outgoing port for the service, which has to map down to the corresponding container port we have configured in the containers that should receive the traffic based on label selection. So target port in the service will likely always be the same as the container port in the pod. Keep in mind the containers running inside of a pod can define more than a single container port. So therefore, you have to select the right one that needs to receive that traffic. Just for the purpose of the exam and for speeding things up, for you to save some time, there are multiple configuration options and imperative commands that you may find useful. One of the imperative command is the -- expose command, which can be used together with the run command. Effectively, this will create a pod and a matching service, which already has label selection and port mapping set up properly. So that is super useful if you want to get a starting point. The command in the middle that you see here on screen is the command for creating just a service by itself. And you can probably see that there's the port mapping. There's no label selection defined here, but that is something that you would be able to customize in the YAML manifest. And there's an additional portion here that I haven't mentioned yet, which is the type of the service. In this case, we're talking about a service type cluster IP, and I will mention what that means exactly on one of the following slides. So let's first have a look at a YAML manifest of a service. Now you can see the two different portions that I mentioned before. One is the label selector, which effectively then selects the pods to route the traffic to. And we have a port mapping from the incoming port to the target port. Now you can probably see here that I'm not defining a specific service type. And what this basically means, if I were to create that object from the YAML manifest definition, is that it will fall back to the default service type, which is called cluster IP. So cluster IP is the most low-level service type we can assign, and effectively what that means is that this service is only reachable from within the cluster. So that means only other pods running in the cluster can actually make a call to it. If you were to try to make a call to that pod from, to that service from outside of the Kubernetes cluster, it would not be able to reach it. Now, cluster IP is super useful for microservices that need to communicate with one another, but oftentimes you will also want to expose your service to the outside world. So to any consumers that want to make a call to the service so it can actually reach the application running inside of the Kubernetes cluster. We have two different service types that you can use for that purpose, node port and load balancer. I would say node port is primarily meant for development staging environments where you quickly want to test something against the service, where you will want to make a call to it, not necessarily from a pod inside of the Kubernetes cluster, but from an end user's perspective. And then load balancer is the option we can usually choose from in cloud provider environments, where we would provision an external load balancer, which will then provide you a public IP address that we can use to make a call to it. Now, I will explain the differences between node port and load balancer in more detail. I would say load balancer is definitely the production-ready service type, but later on, we'll also talk about the ingress, which you will likely want to use instead of the load balancer specifically. Now you can think of the different kinds of service types as almost as onions in a layer of onions. You can see in the middle here, we have the cluster IP service type, which is only reachable from within the cluster. If you were to configure a service with type node port, that effectively means we're exposing it to consumers outside of the cluster, but at the same time, you can also reach it with the same means that you have for cluster IP. And then you can see the most outer layer is a load balancer, which not only exposes the service as the public IP address assigned to the load balancer, but also it's reachable with the help of node port and cluster IP. So that's something to be understood. Here I have a couple of visualizations on how the different service types play out in practice. So you can see here the service type of cluster IP can only be reached from another pod. You would usually use the cluster internal IP address that is being assigned to the service. There are also other ways to basically reach that service in more detail. Now you can see here one example of a object that has been created with type cluster IP. At runtime, the cluster IP will actually be assigned, in this case, 10.96.254.0. This is something that Kubernetes will add as soon as you create the object. And then as a result of that, we can try to make a call to it, in this case, from another pod running inside of the cluster. All I need for this is the cluster internal IP address, the port. So that would be the incoming port that we define for that specific service. And in combination with those two things, I can make a call to it. And again, it would not be reachable from outside of the Kubernetes cluster. Now, using the cluster internal IP address is somewhat tedious. And we don't necessarily want to use that as something that is human readable. The better option is, in fact, to use one of the two options that I will show to you here. Option number one is that if you were to create a service and later on create a pod in the same namespace, it will automatically receive environment variables, which will be provisioned for you as part of that container. So that is one option, how to read it. The probably better option is to simply just go with the DNS name that will be created for you every time you create a new service. So the underlying cluster component in Kubernetes is called core DNS. And core DNS is responsible for mapping basically the service name to the cluster internal IP address, so you can use the service name instead of the IP address, which makes it far more convenient to actually make a call to it. So if you try to make a call to the same service that I mentioned before, you can simply just use that service name ecoserver. If you wanted to make a call across multiple namespaces, then you can spell out the namespace here as well. That would be the second portion of that string. And then the remaining thing that you see here, service.cluster.local, is something that is primarily being provided by core DNS. It's configurable, goes beyond the scope of the exam, but ultimately here is what we can use. Here's one example for the node port service type. The important difference is here is that we cannot reach out to the cluster internal IP address that we've seen for the cluster IP service type. We actually have to use one of the public IP addresses of any of the nodes that are part of the Kubernetes cluster, which you can easily find out by running a kubectl get nodes command, which lets you inspect the details of those nodes. Now, there will also be a node port involved, and that is the main reason why that service type is called node port. You can either assign a static port number or let Kubernetes decide from a range of port numbers. And in combination of those IP address of the node plus the node port, we can make a call to it from outside of the Kubernetes cluster. So let's have a look at a runtime representation of a service of type node port. You can see that the node port has been assigned down there in the ports section. And just to show you how this would look like, so we would use that node port, which is a different value under the ports column if you were to list the details of that service. And you can see as well that I ran the kubectl get nodes command to find out what the IP address is for that specific node. It doesn't have to be the node, by the way, that the pod runs on. That's completely independent. The traffic routing will happen in Kubernetes no matter what. But generally speaking, we would have to pick one of those IP addresses. And lastly, here's one example for the load balancer service type. Just be aware, this is much easier to be used in a cloud provider environment, where the cloud provider will basically provision a load balancer for you, which then will receive a public IP address. There's support for using load balancer in a on-prem Kubernetes cluster, but you would have to install additional extensions to Kubernetes. And as you can see here, there's another value that represents that public IP address called load balancer IP. So that would be the IP address that we would be using. And you can see we would use the public or external IP address that is available in this column, external IP, plus the incoming port of that service to make a call to it from outside of the Kubernetes cluster. So with that, I would say let's give this a try. I see there's a question. I will get back to that pretty soon. But in the meantime, I will let everybody try this out. So we'll give 10 minutes for this one. And here we want to create a service of type cluster IP in the first place, and then we want to switch it to a node port and play around with the different ways we can access that service. If you were to use Minikube, there's a little bit of specialness. So click on this link here that will tell you all about it, but I will also demonstrate that on my machine. Alrighty, so let's have a look at the solution. I'm going to go there. Let's see what that was. We'll go to number 29 here. Clear. And the first thing we want to do here is to create a service of type cluster IP. I'll keep that fairly simple and straightforward. We'll simply just go with the imperative command here. We'll just map port 80 to the underlying port 80 in the container. If we were to list the services in the default namespace, you should be able to see my app service. You can see that we have the cluster internal IP address and the incoming port 80. Now we of course also need to have an application that will allow us to basically run something. So I'm just going to create something here quick. That is a deployment that manages one single pod. You can see that we're also mapping this to port 80 so it can actually receive that traffic. Internally, by the way, label mapping, label selection will be set up properly simply because I went with the same name here for the service and the deployment. In turn, it will simply just assign a default label, which will be matching right here. Now you can definitely modify that more if you want to, but trust me, that is what's happening here under the hood. And now what we want to do is to actually make a call to it. So we want to make a call from a temporary pod to the cluster internal IP address and the incoming port here, which is port 80. In fact, we don't need to spell out port 80. That would be the default anyway, but it seems like it's working. And in the same kind of way, we can also use the my app DNS name. We don't have to fully spell out the full string that you've seen on my slides, simply because we're calling that service from within the same namespace. But if I were to basically create the temporary pod in a different namespace, that would not be possible anymore. We would have to spell out the other namespace. Let me see if I have T23. Let's go with that one. So let's say I were to use a temporary pod in T23, and I will try to make a call to it. As you can see here, that wouldn't work. What we need to add here is the namespace that this service runs in, and then it would effectively be able to make a call to it. And as a side note, if you wanted to spell out the full thing, it would have the same effect. So service cluster.local would mean the same thing here. All right, so now what we want to do, we want to change the type of service for that object. Okay, added service. And this one was called my app. in the default namespace, and we're going to turn cluster IP, as you can see here, to node port. And that will effectively be reconciliated by Kubernetes, which means it will look at the changed data and then will reflect that in the existing object. Now you can see here the cluster internal IP address is still available. So we could still make the call to that same service the same way as we did before. But we did receive a node port that we can now use to make a call to it from outside of the Kubernetes cluster. Now, usually you would do the following. You would have a look at the nodes and their IP addresses. So for example, here the external IP address. Unfortunately, Minikube runs in a virtual machine, so the external IP address would not be available. But there's a little workaround for Minikube, which you can have a look at when you click on this link in the documentation here. We can expose a service with a specific URL, and I can do this in a different terminal window here. So I can say here, we want to provide a public URL for the service with the name my app, sorry. And I can use this one here instead of the non-existent external IP address to basically make a call to it. So basically that's tunneling towards that service. And that is basically just a little workaround for Minikube in general. If you were to have the public external IP address here for one of your nodes, not a big deal. You could simply just use that. All right, so I think that's what we wanted to do here. Do you have any more questions about services so far? All right, we have about half an hour left. So let me make sure that we still get through the remainder of the topics that are going to be important. What do you need to understand for the exam? You need to understand the different kinds of service types, cluster IP, node port, load balancer. In fact, there's another service type that I didn't even mention here, but I didn't put that into the slide deck simply because it's not going to be necessarily relevant. You can definitely read up on that in more detail, but we can basically expose our applications using the service primitive and then route traffic either from within the cluster or outside of the cluster. Now, just a couple of words about troubleshooting services. There are two different breaking points that I wanted to mention here, which we've been talking about before as well. So if you notice that you cannot connect to that service, or if the traffic could not be routed to the pods that you expected to be routed to, then you will want to dig in a little bit deeper. So the first test would be try to make a call to it with the temporary pod. And then what we should probably also have a look at is the endpoint. So endpoints is a Kubernetes primitive that gives us information about the IP addresses and the ports of pods that we have assigned here as the receiving end of a service. So if you see none under the endpoints column, that effectively means that traffic routing has not been configured properly in the service object, and therefore you would need to have a deeper look. What you will want to see, though, is the IP address and the ports as mentioned here. So this one basically routes traffic to two different pods in this case. Now, there are two different breaking points. One is the label selection, and the other one is the port mapping. I already mentioned them in more detail. You can see here, make sure that the configuration in the service matches with the configuration in the receiving pod, and not only just for label selection, but also the proper port mapping. And one more side note, and we'll talk about network policies pretty soon, is that network policies could also play a role in blocking the traffic from one pod to another one. So if you're already familiar with network policies, you may know that they can be defined to basically block that traffic. So if you think that port mapping looks correct, label selection looks correct in your service, and you don't have any more other idea, then maybe the reason may be a network policy. And we'll talk about network policies pretty soon. And just make sure that the pod also works as we've shown before. So we'll skip over the troubleshooting scenario. You can definitely try that at home. Given that the question already came up earlier in the attendee chat, I definitely want to spend some time on the ingress primitive. So the question was, how do we map a domain name basically to a load balancer, I guess? How do we make this publicly available to end consumers so that they don't have to use a public IP address? Which is definitely very inconvenient. This may be fine for internal consumers within the company, but for anyone like a public web page, that is definitely not super useful. And that is one of the reasons why we have the ingress Kubernetes primitive. It lets us configure external access to a service or multiple services with the HTTP or HTTPS protocol. Now, the ingress should not be confused with a service of type load balancer. What it effectively does, it routes traffic to an existing service. And the way it routes traffic to it is using a specific set of rules. You can, in fact, route many different, you can actually define multiple URL context paths, which will then route traffic to a bunch of different service objects. And the main reason, or one of the main reasons why we have the ingress, is that setting up load balancers for any application that you want to expose publicly can become fairly costly. So every time you provision an external load balancer, your cloud provider will charge you for it, or you have to pay for it in some other form. So instead of doing that, we can basically have one entry point, which is that ingress, which not only can route traffic to one single service inside of the Kubernetes cluster, but to multiple. The default mode of operation for the ingress is to use HTTP, but you can also configure HTTPS, so basically referenced as TLS termination in the documentation. But keep in mind, TLS termination is out of scope for the CKAD. It's only going to be relevant for the CKS. So if that's something that you're planning to take in the future, have a look at that in more detail. Now, the ingress will be evaluated by a so-called ingress controller. The ingress controller is an external component that we need to install into the Kubernetes cluster. Again, think of Kubernetes as a platform. They basically provide a specification of how ingress could be implemented, and then external providers can provide their own implementation for the ingress controller, which is the case right now. So if you look at the list of ingress controllers, you can see there are a whole bunch of different ingress controllers. And you, as probably the admin of the Kubernetes cluster, have to decide on one specific implementation or potentially multiple of them. Now, you can install multiple ingress controllers into the Kubernetes cluster if you want to. One of the popular ones is the Nginx ingress controller. So let me see where I find that here. And that is also the one that we are going to use as an example. So this one is a open source implementation, I believe. And it's free of charge. I'm not quite sure if I can find the right documentation here at the moment. But not only does it do the traffic routing, but it also provides additional features that are product specific. So if I were to use ingress controller annotations, you'll actually see there's advanced configuration that we can provide to the ingress definition. Now, any more advanced configurations that are provided by specific implementations of the ingress controller are triggered, or I shouldn't say triggered, are configured and set using annotations. Now you can see here, those annotations are completely product specific. If you were to switch from one ingress controller to another one, you would have a different set of annotations again, which is a little bit clunky. And that is also one of the reasons why the CNCF Foundation came up with the replacement API for the ingress called the Gateway API, which provides a more uniform specification for this kind of functionality. But for now, for the CKAD, only the ingress is going to be relevant, not the gateway API. This has already been changed in the CKA certification, and likely it's going to trickle into the CKAD as well. Now, coming back to a higher level visualization of the ingress and how it fits into the picture. Now you can see here that I defined a ingress object. The ingress object will be evaluated by the ingress controller, which I don't show here in the visualization, but that is what's happening here. And you can see the ingress is routing traffic to different services. One will be reachable when the consumer adds the URL context path /app, and the other one will be reached when the end user uses /metrics. And depending on what has been requested, traffic would be routed. Now, one important thing I haven't mentioned yet is that the ingress will also provision an external load balancer for you, specifically in cloud providers, so that you have that public IP address available. So you would usually not go with the service type load balancer. You can just go with the ingress primitive, create the object, and it will provision an external load balancer for you. Now, as part of the configuration in the ingress, you may also want to assign a domain name. That has been asked about in the attendees chat. So I think that was what the question was about. For external consumers, you will likely want to provide that external domain name. So how can that be configured? So let's have a look at the configuration and the creation of the ingress object. What you can see here is the imperative command. The imperative command is a little bit clunky. You can see that the rule is relatively long. So I would usually like to explain the ingress with the help of the YAML manifest instead. As you can see here, we have a ingress YAML manifest, and this ingress YAML manifest has the optional definition of a host name. So that is basically that domain name that the person attending here was probably asking about. Ultimately, here for this ingress, we are defining one or many rules. So effectively, we want to route traffic for that host name. And this host name should basically route traffic to a so-called backend. The backend is effectively the service, including its DNS name and its port. And then this one should be reached every time the end user uses the URL context path Corellian/API. Let me see what else I could explain. We'll skip over that for now. And here's one more point on the DNS name for the ingress. So if you were to decide to use a host name, then you will still have to configure that DNS entry to the external address, so the mapping between those two. And for that, you would have to configure a record or a CNAME record. There's another project as part of the CNCF landscape called external DNS, which can help you with managing those DNS records for you in local installations of Kubernetes. So when we are practicing for the CKAD, it's usually not necessary. You can configure that mapping from the DNS name to the external name. In this case, it would be localhost in your etc hosts file. So that is a way to basically play around with that. And then once you have that configured, we should be able to make a call to it. So let's actually try this out in practice. And that would be number 31. At least this one I want you to play around with. I'll make this a little bit smaller. I'll give you 10 minutes, and then we'll spend probably the remaining 10 minutes on network policies. All right, so let's have a brief look at this. Question came up on Minikube and the add-on. We'll close up this one. So you can always install or check on add-ons in Minikube with this one. There's one for Ingress here, currently disabled. So we'll enable that for now. So Minikube add-ons, I think it's install, now add. Let me see what the command was. Enable Ingress. And you can see that will install the Ingress Nginx controller, which will then be able to check in the corresponding namespace. So that will take a little bit of time. In the meantime, we can probably here say get namespaces, and there should probably already be something like Ingress Nginx. So if you say, give me the pods in the namespace Ingress Nginx, you should be seeing something that is running. Okay, so that is already set up properly. All right, and now we are just going to go through the motions of creating a starting point, which is just a deployment. Before I do so, let me delete the deployment I already had in place here. And the same thing for the service, delete service my app. Now we'll get started by creating a quick setup here. I'm not going to talk about it anymore. That's pretty much the same what we've done before. And just to verify that we can actually make a call to it, that the setup is proper, get service, and let's make sure that I can make a call to it. So it's at least functional. So you can see this one is running on a different port, 3000. So that is accessible from within the Kubernetes cluster. Now we want to set up my ingress. And I'm just going to copy paste that from the solution here, just to speed up a little bit. You can see here, we are defining the host name hello-world.exposed. It routes to the backend with the name web and on port 3000. And up here is one example for such a Nginx ingress annotation. So let's do that. Oops, ingress.yaml. And let's have a look at the existing ingress here. At some point of time, you'll actually see that the IP address here is going to be populated. That is going to be the public IP address. This will likely not happen until we open up the tunnel to it. Another thing we will want to check is if we have the entry for hello world in my etc hosts file. So that basically needs to map to localhost. Let's see if I got it. So, so it's already here. So that is already pre-configured. That's an entry you would need in your local etc hosts file. Let's have a look if that's going to be populated. Not yet. So I guess we still have to do something. We'll have to basically set up the Minikube tunnel, which is something specific again for Minikube, unfortunately. Make sure that you commit that with your password, otherwise it won't expose it. But effectively, that makes available that service. And you can see now at some point, this IP address should be populated, so you should be able to make a call to it. So now what we want to do is to make a call using curl to the domain name that we configured here. And that should at least respond with hello world or something else. And it looks like we could properly route the traffic here. All right, any more questions on the ingress so far? So unfortunately, we are running out of time. I don't think we'll really have time to talk about the network policies anymore, but at least I want to give you a quick overview on what network policies do and what you need to understand for the exam. So that would have been the last topic for today, either way. If you have any questions you will still want to ask, put them into the attendees chat or the Q&A box now so I can read them out aloud. But generally speaking, as you can see here, network policies, last topic. Effectively, what is important to understand about network communication within the cluster is that any pod can talk to any other pod within the Kubernetes cluster without any restrictions. So therefore, for security reasons, it's likely a good idea to basically put in place so-called network policies. Network policies effectively act as firewall rules, but for the pod-to-pod communication. So again, here you will need a so-called network policy controller. The one that I would have been using is Cilium, but there are definitely other ones available. So you can definitely check those out as well. And roughly, if you want to get a first impression on how network policies look like, it again works based on the concept of label selection. You will have to basically define which pods this network policy should apply the rules to. And you can see here, it should apply to all the pods in the same namespace that have the assigned key value pair app payment processor and role API. And then you have specific rules for incoming traffic and outgoing traffic between those pods. So you can see here, ingress has a specific section and egress would have a specific section. I'm not going to talk about that in more detail, but let me give you some more information on how you can effectively learn more about it. One resource I found super helpful is this one here specifically. That is a GitHub repository that not only visualizes different kinds of scenarios, but it also walks you through them. And I would say that's probably a very good a resource to effectively learn more about network policies, how to configure them, how to put them together, because I'm pretty sure it's going to be a topic in the exam itself. Now you can see here for each of those scenarios, you can basically get a little visualization, and it even gives you the individual commands and YAML manifests that you need to try out. So I would suggest spend some time on this to become more familiar with the concept. So I think it's super useful. And then if you want to visualize some of the rules that you may want to set and want to just grasp if the network routing works as expected, I can suggest to you the networkpolicy.io webpage. That one lets you post a definition of a network policy, and this would be then visualized in the top part of that web page. So super useful. All right, so I would say try this one at home, play around with that concept. It's definitely going to be more important. And I think that's all I got. Top of the hour, unfortunately, we are running out of time. If you have any more questions you would like to address, do let me know. Happy to stay on for another 2 or 3 minutes. If not, as I mentioned on day number 1, feel free to send me an email. If you have more specific questions or you want to discuss something, do let me know. You will find my email address in one of the first slides in my deck. And here's one question: how long will the sandbox be available? So I guess you're talking about the O'Reilly Interactive Lab sandbox. This will never go away. You will have access to it as long as you're a subscriber to the platform. When you say a sandbox, maybe you're talking about my GitHub repository that will also stick around. So that is not going to go away. All right. Looks like there are no questions right now. All I can say is good luck with your own exam. Do let me know if you feel like anything should be changed in my slide deck, or if you would like to see more information about something else. And yeah, that's all I got for today. Unfortunately, I'm running out of time. And with that, I'll give it back to Brittany.
All right, thank you so much, Benjamin, and everyone who participated in today's course. We hope you benefited from the live course and hope to see you on other O'Reilly live courses in the future. Thanks again. Enjoy the rest of your day. Goodbye, everyone.